Welcome to cross sections of a cube. We will be looking at the intersection of cubes and planes, non-empty intersections. For instance, down here we have this cube. We have a green mesh flat plane, at least part of it showing here in a certain coordinate system. And the intersection of that cube and plane, at least in this picture, is a triangle plus its interior. So the general question is going to be the following. When a plane intersects a solid cube, what does the intersection look like? In general, this intersection will be a polygonal region. A polygon, which is the perimeter, plus the interior of that polygon. That together will give us a polygonal region. As an illustration, let's look over here. We have this cube, as we can see. We have part of a plane shown here, kind of a light green mesh, and this plane intersects this cube in a triangular region, more or less in dark green right here. The intersection region will be a triangular region, including the interior. In this particular case, it's a triangle, but we possibly, with different planes at different places, could get different polygons. So part of our setup is the cube. We have a cube, three-dimensional cube, and if we look at the vertices, there are 8 vertices. The coordinates of each vertex, the x-coordinate is either a plus or minus 1, the y-coordinate is either plus or minus 1, and the z-coordinate is either plus or minus 1. For instance, this vertex right here has coordinates minus 1, minus 1, minus 1. To set up our problem, first we will draw a line L going through the points minus 1, minus 1, minus 1, and 1, 1, 1. So in three-dimensional space, we have a line L, and it has a point minus 1, minus 1, minus 1 somewhere, and 1, 1, 1 somewhere else. So now, at each point t, coordinates t, on L, let's draw a plane through that point perpendicular to L. This plane will intersect the cube, and the intersection will be some two-dimensional polygon within that plane. The type of polygon it is, whether it's a triangle, square, hexagon, or whatever, can be different at different values of t, at different points t on that line where the intersection is occurring. So let's look at one of the cross sections. Here is the line L and the cube, and if we take a plane maybe right about here intersecting the cube, that cross section will be a triangle. If we increase the value of t so that we're looking at a point on this line L that is further along this line going from left to right, and the plane at that point perpendicular to that point intersects the cube, we could get a hexagon shown here. So that's a possibility too. Here is a short video showing successive cross sections as we go along that line through the two vertices and looking at intersections of planes perpendicular to that line with this solid cube. As you could see, as we started off, the cross sections were triangles, then they changed to hexagons, and then back to triangles. Let's try that one more time so we can see what's happening again. So we start off with the cross sections being triangles, and that goes on for a while, and then after a while it changes to hexagons. Right there's still a hexagon. Now it's changing back, I guess, to a triangle, and it continues as triangles until you get to that upper right hand vertex. So the mathematical problem is to show mathematically that the intersection of these planes that are perpendicular to that line L and the cube can only be, in our particular problem, triangles or hexagons. If we took a different line L, we might get a different answer. The type of polygon can be different for different values of t, or different points with coordinates t, t, t on that line L. And what we would like to do is to see how we can write a program to illustrate what is happening in this setup using Octave, or almost equivalently MATLAB. In general, with our mathematical investigation of this type of situation, we will see that some intersections of planes with the cube might be triangles. It could conceivably, in some cases, not ours, be a square or some other polygon. And our calculations will tell us that what type of polygonal region that we have. So what we need to do to solve this problem mathematically is first to be able to find the equation of a plane. We'll review that. We've seen planes in other videos in this series. And secondly, find the intersection of a plane with that cube. So first, let's review equations of a plane. So let's suppose that we have a plane P, and it satisfies the following. It contains the point x0, y0, z0 with those coordinates, and we have a vector n which has coordinates a, b, c, which is normal, which means perpendicular to that plane P. So how do we find the equation of this plane? What we'll do is pick a point, maybe right here, with coordinates x, y, z, perhaps at the end of this arrow, and figure out what the coordinates x, y, and z have to satisfy. So here's a picture that we saw before. We have this plane P. We have a point x0, y0, z0 in that plane. We have a normal n to that plane. And we have a point, an arbitrary point x, y, z somewhere in that plane. So as we said before, we'll let n be the normal to that surface, an orthogonal vector orthogonal to that surface. And let's let v be the vector going from x0, y0, z0 to this point x, y, z. So the components of that vector are x minus x0, y minus y0, z minus z0. In that case, the vector n and this vector v are perpendicular. And that tells us that the dot product of those two perpendicular vectors has to be 0. So what does that mean? It means the vector n, which has components a, b, c, times the vector v, which is this stuff, equals 0. Now let's remember how we take the dot product of two vectors. It's this component times this component plus the second component times the second component here plus the third component times the third component here. So this vector equation can be rewritten as a times x minus x0 plus b times y minus y0 plus c times z minus z0 equals 0. So this is one way that we can write the equation of that plane. So let's see what we can do with this. as an example. Let's find the equation of the plane containing the point 1, 3, minus 2. That's basically the x naught, y naught, z naught here, and perpendicular to this vector 6, 2, minus 3. We can say that this plane is perpendicular to this vector, or equivalently, we could say that this vector is perpendicular to this plane. So let's see how we can solve this. Our solution is first, here's the equation of the plane that we saw before in a general form. And a, b, and c, according to this, the components of our normal vector are 6, 2, and minus 3. The x naught, y naught, and z naught values are the values of this point here, which is 1 minus 3, 2. So what we'll have in that case is this will be x minus 1. This part right here will be x plus 3. X minus a minus 3 is x plus, y plus 3, sorry, y. Minus, and then here we'll have z minus 2. So we substitute in the values of a, b, and c, and also the values of x naught, y naught, and z naught into that equation. So here is the equation of that plane. So let's consider this problem. We have the line L, which is going from minus 1, minus 1, minus 1 up to 1, 1, 1. And we want to find the equation of the plane perpendicular to that line and containing the point T, T, T. So the plane contains that point with coordinates T, 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 and it's going to be perpendicular to a vector n here, which we can think of, if we shrink it down to size, we can think of it as being 1, 1, 1. The components of the vector n are 1, 1, 1. So the solution then is just going to be 1 times x minus t plus 1 times y minus t plus 1 times z minus t equals 0. And this can be algebraically simplified to z equals 3t minus the quantity x plus y. So let's now find the intersection points for the cube that we've been discussing and the plane containing the point TTT, which is perpendicular to that line L. So what we want to do is to solve the following system of equations and inequalities. We want z for a point on this plane to satisfy 3t minus the quantity x plus y. We saw before that that was the general equation of a plane going through the point TTT and perpendicular to the line L. And because we want the point xyz of that intersection to be inside the cube, x will have to be between minus 1 and 1, and so will y, and so will z. So here's our situation again with the plane shown in green mesh here. And the intersection, that's actually blue, but it doesn't look too blue here, is some polygon. In this drawing, a triangle. So we want to find the boundary of this polygon. And here's what we can notice about this thing. First of all, the edges of this small triangular region are embedded in some faces of the cube. For instance, this edge right here is in this face of the cube over here. The vertices of that triangular intersection are on some edges of the cube. For instance, this vertex right here of the triangle is on this particular edge of that cube. So edges of the triangle are on faces of the cube, vertices of the triangle on edges of the cube. Okay, so let's focus on the second statement. The vertices of the triangle or polygon lie on the edges of the cube. Okay, so let's see what we can do with that. Let's let E sub 1 be this edge of the cube, joining the vertex minus 1, minus 1, minus 1 to the vertex up here, minus 1, minus 1, 1. So the only thing that changes is the z coordinate. Down here, z is minus 1. Up here, it is plus 1. The x and y coordinates don't change on this edge. So we can say that E sub 1 is a set of points x, y, z such that x and y are both minus 1 and z has to be between minus 1 and 1. So can there be a vertex? When will there be a vertex on this edge E1? Well, first of all, let's remember that the equation of the plane containing this polygon was z equals 3t minus the quantity x plus y. So if you're looking just at this edge here, where x and y are both minus 1, that says that if z equals 3t minus the quantity x plus y, z is 3t minus the quantity minus 1 plus minus 1, which simplifies to z equals 3t plus 2. But let's remember that z has to be between minus 1 and 1. So that says that 3 plus 2 is between minus 1 and 1. If we subtract 2 all the way through these inequalities, we get minus 3 is less than or equal to 3t is less than or equal to minus 1. Dividing these inequalities by 3 tells us that t is between minus 1 and minus 1/3. So if you are looking at that line L once again, you will get a vertex of this polygon on the edge E1 if t is between minus 1 and minus 1/3. Okay, so we found out what it takes in terms of t for a vertex of our intersection polygon to be on edge E sub 2. We can also look at the other edges of this cube. There are 12 edges, aren't there? On the bottom you have 1, 2, 3, 4. On the top you have 1, 2, 3, 4. And vertically 1, 2, 3, and 4. We can define E sub 3 and E sub 4, E sub 5, E sub 6, E sub 7, and E sub 8, kind of similarly to the way we did E sub 2. If we look at E sub 3, it will be the set of points x, y, z, such that x equals 1, y equals minus 1, and z can be anything between minus 1 and 1. To find out where that is in this diagram, first of all, we have that x is 1, y is minus 1. Well, right here, we have x is equal to minus 1. If we move over this direction, here's x equals 1. Y equals minus 1 is also right here. We don't move in this direction because that would change y. So y is minus 1 here, and z can be anything between minus 1 and 1. So E3 is this vertical edge here. Similarly, we can find E sub 4, which is right here. E sub 5 is here. E sub 6 is here. E sub 7 is here. And E sub 8 is right here. And so what we do is solve inequalities similar to what we saw in the E sub 2 case. And what we do find is that we do have a vertex of that intersection polygon on E3 for t values between minus 1/3 and 1/3. On E4, if t is between 1/3 and 1. On E sub 5, if t is between minus 1 and minus 1/3. On E sub 6, as t is between minus 1/3 and 1/3. E sub 7 if t is between minus 1/3 and 1/3, on E sub 8 if t is between 1/3 and 1. We also have to find out what happens on E sub 9, 10, 11, and 12, and we'll do that momentarily. Similarly, again, we can define E sub 9 to be this edge of the cube, E sub 10 to be this edge, E sub 11 is this edge, and E sub 12 is this edge up here. And if we do that, what we find is for E sub 9, which is right here, when we intersect the cube and a plane perpendicular to that line L that we talked about at the point TTT on the line L, we will get a vertex of the intersection polygon on E9, on this edge E9, if t is between minus 1 and minus 1/3. For E sub 10, we get an edge if t is between minus 1/3 and plus 1/3. On E sub 11 down here, if t is between minus 1/3 and 1/3. And on E sub 12 up here, if t is between 1/3 and 1. This slide summarizes what we have seen before. E sub 1 is an edge of that cube. The cube, remember, was the set of x, y, z, where x, y, and z ranged between minus 1 and 1 for all three coordinates. So E sub 1, that edge, was the set of points where the x-coordinate was minus 1, the y-coordinate was minus 1, and the z-coordinate could range anywhere between minus 1 and 1. Well, in that case, the intersection polygon has a vertex on E1 if t is between minus 1 and minus 1/3. Similarly, E sub 2, defined as before, the intersection polygon in that case has a vertex on E2 for values of t between minus 1/3 and 1/3, and so on for all 12 edges of that cube. So now, if we consider what we just saw, we can rearrange our, I guess you can say, accounting of what happened in terms of t instead of in terms of edges. If t was between minus 1 and minus 1/3, then the intersection polygon has vertices on the edges E1, E5, and E sub 9, so that intersection polygon must be a triangular region. Similarly, if t is between minus 1/3 and 1/3, the intersection polygon has vertices on these edges, E sub 2, 3, 6, 7, 10, and 11. So 6 vertices on these 6 edges. So the intersection polygon is going to be a hexagonal region. And finally, if t is between 1/3 and 1, the intersection polygon is going to be a triangular region. And in conclusion, we can say the following. In the problem that we looked at with the planes intersecting the cube, the plane containing the point t, 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 its coordinates, we can say that as t varies between minus 1 to minus 1/3, the intersection polygon, the intersection of the cube, solid cube, and the plane is a triangle, including its interior. As t varies between minus 1/3 to 1/3, the polygon changes to a hexagon in that range of t values. And as t varies between 1/3 to 1, the polygon of intersection once again returns to be a triangle. Thank you for watching this video. I hope you found it informational and also enjoyable.